Dear students, for today we'll see the fourth point in our first unit, that is basis of electronic components. In that we will see active components, in which we will see MOSFET, SCR, DIAC and TRAIC. So this will be the part 2 of active components, because in the part 1 we have studied diode, Zener diode and BJT, and now we are going to study MOSFET, SCR, DIAC and TRAIC. So here the names of the active or components which we are going to study. First one is MOSFET, which is called as metal oxide semiconductor field effect transistor. It comes under the group of FET. Now FET will be basically are classified as two types of FET. One will be JFET, that is a junction FET, and another one is MOSFET. So from that we are going to study here what is MOSFET. Then second one we are going to study SCR, that is silicon controlled rectifier. Third we are going to study DIAC, and fourth we are going to study TRAIC. So let's start with the basic definition as we had seen in part 1. What are these active components? So active components deliver power or energy to the circuit. They will not consume power, they will not dissipate power, they will not store power, they will not consume energy, they will not dissipate energy, they will not store energy. They will deliver, they will give. Okay, so they produce energy in the form of voltage or current. Active components can control the flow of current. They are capable of providing power gain. Active components are energy donor. They require an external source for the operation. Okay, so these were the basic things what we had seen for active components. Then we'll go to see the first active component of part 2, that is MOSFET, metal oxide semiconductor field effect transistor, or it is also called sometimes as metal oxide silicon field effect transistor. It is known as MOSFET. It is a unipolar transistor. A unipolar means the current conduction which takes place in this device is of only one type of charge carrier. Because in semiconductors, we'll be studying two types of charge carrier. One is electron, negative charge carrier, and one are holes, will be positive charge carriers. So here in MOSFET, you will be having unipolar. Unipolar means the only one, either electrons or holes, will constitute the flow of current. It is used as an electronic switch and to amplify electronic signals. The device has three terminals are consisting of source, gate and drain. Apart from this terminal, there is a substrate which is called as body, which is always connected to the source terminal for practical applications. And therefore, as a whole, instead of four terminals, we say that MOSFET has three terminals: source, gate and drain, where source will be internally connected to the body or the substrate. Then if you see the structure of a MOSFET, so here you can see you will be having a body here down. This is the body, which will be a lightly doped p-type or n-type semiconductor. This is the body. Okay, now in that body you will be inducing a high opposite type of semiconductor, here, which will be taken as source. This will be taken as source, and here also it will be opposite to the body type of semiconductor. This will be taken as drain. This will be taken as drain, and this body was your substrate. It can be called as substrate, or it can be also called as body. Okay, so this body will be internally connected to source. This body will be internally connected to source. Okay, now a current has to flow from source to drain, like this it has to flow, and we require a channel to make the current flow. And that occurrence of that channel, or the increase or decrease of the current flow, will depend on what voltage we give at the gate terminal. This is the gate terminal. Okay, so gate terminal is connected to a metal here. This is a metal. Okay, and then after the metal you have SiO2 layer, which is an insulator, oxide layer. This is oxide layer. Okay, and then you have here semiconductor. semiconductor, okay, which you use for drain or source. And then what is the body? Okay, so body semiconductor will be there as a semiconductor part for the gate on the other side. So gate will have metal, it will be having a oxide layer, and then it will come in contact with semiconductor. So here only the name of MOSFET comes, it is a insulated gate. So you have metal oxide semiconductor. Then it is field effect transistor. Okay. So here this is the three terminals are gate, drain, and source, which are important. And the bay or the body or the substrate is internally connected to the source. So practically, if you go to see in your labs and all, if you see FET, you will get of this type. And then you can see the three terminals which have come, source, drain, and gate. And those three terminals you can use for your connections. Now, if you see the classification of MOSFETs can be basically classified into two types. One is called as enhancement type and the other one is called as depletion type. So here you have enhancement type. This is enhancement type. Okay. Now here between source and drain, there will be initially no channel, no channel. But then as you apply the gate voltage, channel can be produced and then current will flow between source and drain. And second type you have depletion layer. Here between source and drain, channel will be present and the flow of current through the channel between source and drain will be varied according to the voltage applied to the gate terminal. So gate terminal will be the a controlling terminal. Okay. And further, this both will be uh, subdivided as N channel and P channel. So here you can see you have enhancement N channel MOSFET, you have enhancement P channel MOSFET. Here you can see you have depletion N channel MOSFET, you have depletion P channel MOSFET. Okay, so totally four types we are having here. So here you can see enhancement type we have two and depletion type we have two. So totally four types of MOSFET. Okay, MOSFET will be having. Then after that, we'll go to see the same thing, or classification, how we have done. The MOSFET is classified into two types based on the type of operations, namely enhancement mode MOSFET, where the channel will not be existing initially. Afterwards, it will exist as you give the gate voltage. And second one is depletion mode MOSFET, where the channel will be existing. And if you give the gate voltage, the current from source to drain will be varying. These MOSFETs are further classified on the basis of the material used for construction, as it can be N channel, your N type of semiconductor used, or it can be P channel, your P type of semiconductor used. So in general, there are four types of MOSFETs: N channel depletion mode MOSFET, P channel depletion mode MOSFET, N channel enhancement mode MOSFET, and P channel enhancement mode MOSFET. So these four we have seen. So here we'll see the structure of P channel, enhancement type and depletion type MOSFET. So on top you see the first one as enhancement type, P channel. P channel. Channel means it will be a channel between source and drain. And here second one you can see depletion type, okay, P channel, P channel. Now in P channel, what happens? The body which is lightly doped will be of N type semiconductor and source and drain will be of P type semiconductor. Okay. Similarly here, the body will be of N type semiconductor and source and drain will be of P type semiconductor. In a depletion type, the second one what I've shown, there is a channel which is there between source and drain. This is existing. Whereas in enhancement type, the channel is not existing. This channel will be occurring afterwards, after you gave the gate voltage. Okay, the P channel will exist afterwards, but initially it is not existing. And here you have an insulated gate. Here also you have an insulated gate. The only difference between depletion and enhancement type will be in enhancement type, initially the channel between source and drain where the current has to flow will not be there. Whereas in depletion type, channel will be there. And that is only shown in symbol here. Because channel is not there, this part is shown as broken part. Even here you can see this part is shown as broken. This gap is shown because gate is insulated. This is the gate terminal. The top one is shown as drain, down one is shown as source, and this is body which will be internally connected to source. Okay. Same thing for depletion type also. There is a insulated gate, but you don't have gaps here because the channel is already existing. Then you have drain here, you have source here, and you have body here. Body will be internally connected to source and gate will be insulated. So this will be your P channel enhancement type, depletion type of MOSFET. Similarly, you can see N channel depletion type and enhancement type MOSFET. So here you can see this. This is the first one, okay, which is enhancement type N channel, enhancement type N channel, and this will be second one, depletion type N channel, depletion type N channel. So here you can see the body is of p-type semiconductor and you have source as n-type semiconductor, drain as n-type semiconductor. So initially there is no channel between source and drain. The gate is insulated. So the symbol shows broken part here and broken part here. And same thing, you have insulated gate, you have drain, you have source, you have body which is internally connected to source. Okay. And in our depletion type, there is a channel existing. So channel will be existing here before applying the gate voltage. And here you can see it is insulated gate and there is no gap here. There is no gap here because channel is already existing. And here you have drain, here you have source, body will be internally connected to source, and you have insulated gate. So these will be the symbols of your enhancement and depletion type N channel. Now, how does the exact symbol look like? Now, in N channel, you see it will be having a broken part for enhancement type here and here. And for N channel, this arrow is going inside. This arrow, which shows from source to drain flow, will be showing inside. Similarly, depletion type N channel also arrow will be shown inside. Okay, and then there will be no gap here. There will be no gap because it is having a existence of channel already in depletion type. Similarly, if you see P channel, the arrow will be moving outside. So the flow of conventional thing from source to drain will be shown outside. This will be shown outside here. This will be shown outside here. And here you will be having a broken a channel, which means that there is no channel between source and drain at the start. And once you apply the gate voltage, afterward the channel will be produced in enhancement type. In a depletion type, the channel is already there, so here you don't have anything. Here you don't have anything broken as such. Okay. Then packages which you can get for MOSFET. First one is shown as surface mount. You can get MOSFET in this type, which is surface mount. Okay, you can get MOSFET as through hole package. You can get MOSFET as PQFN package. You can get MOSFET as direct FET package. Okay, so these are some of the packages in which you get the MOSFET. Then these packages can be described like this. The MOSFETs are available with a different name in each kind of packages as follows. In surface mount, you can have TO263, TO252, MO187, SO8, SOT223, SOT23, TSOP6, etc. Second, for a through hole, you can have TO262, TO251, TO274, TO220, TO247, etc. In a PQFN package, you can have a PQFN 2 into 2, PQFN 3 into 3, PQFN 3.3 into 3.3, PQFN 5 into 4, PQFN 5 into 6, etc. And in fourth type, that is a direct FET, you can have a direct FET M4, direct FET MA, direct FET MD, direct FET ME, direct FET S1, direct FET SH, etc. Okay. Now, there are many applications of MOSFET, but the important ones are MOSFET amplifiers. You can make amplifiers by using MOSFET, which are extensively used in radio frequency applications, that is RF frequency. Okay. Second one is DC motors can be regulated by power MOSFETs. Third one is very important thing, high switching speed of MOSFET make it an ideal choice in designing chopper circuits where switching of that is on and off is important. Then fourth, it acts as a passive element like resistor, capacitor, inductor. So it can also act as a passive component like resistor, capacitor, or inductor. Then we'll go to the next active component, which is called as silicon controlled rectifier, SCR. Now SCR will be made up of 4 layers. So here you can see the 4 layers: P type of semiconductor, N type of semiconductor, again P type of semiconductor, again N type of semiconductor. The P type of semiconductor will be connected to a terminal called as anode. Here will be a metal here. And then the last N type of semiconductor will be connected to a terminal called as cathode base. Okay. The last N type of semiconductor is connected to a terminal called as cathode. Okay. So anode, cathode. Anode will be always positive for proper conduction of SCR. You have to connect this to the positive voltage. Okay, and cathode will be connected to negative. So anode will be more positive than cathode if you want the proper conduction of SCR. Now, because it is having 4 layers, it will be having 3 junctions. The first junction is called as J1, which will be between the first 2p and N type of material. The second junction will be called as J2, which will be between the N and P type of semiconductor. Then J3 will be then again the P type and N type of semiconductor junction J3. Okay. Then the third terminal will have here a controlling terminal will be called as gate, which will be very important in SCR. So SCR as a whole will be having now 4 layers, 3 junctions, 3 terminals, and the terminals will be named as anode, cathode, and gate. Now, same a description will give you. The SCR is a 4-layered semiconductor device that forms NP-NP structure. Either it can be N-type semiconductor, P-type semiconductor, N-type semiconductor, P-type semiconductor, or it can also be PN-PN structure, which eventually forms 3 junctions, J1, J2, J3, because 4 layers means there will be 3 junctions. Among the 3 terminals, the SCR, the anode is a positive electrode. It will be on the P layer. Cathode is a negative electrode. It will be on the N layer. The gate acts as a control terminal of the SCR. Symbol of SCR you can see here. You can see this arrow. So you can see a arrow and a structure same like your diode, but only thing a third terminal will come here. So this will be your positive electrode, which is called as anode on top. So here you can have anode, and this will be negative terminal, which will be called as cathode, and the control terminal in between will be called as gate. Okay, so this is the direction of flow of a conventional current. So this is your symbol for SCR. Then the packages in which you get SCRs are, the first one is shown as a stud type here. So you can see a stud type package. You can see a plastic module package. You can see a discrete plastic, and you can see a press pack. Now, in these packages, it is very important for you to understand the 3 terminals of the SCR, which is anode, which is cathode, and which is gate. Then if you go to say applications of SCR, there are many applications you can have. So here some of the applications I have named. First one is a controlled rectifiers. It is called as controlled rectifier because a normal rectifier which is uncontrolled can be built up with the help of diodes. But if you want to build up a rectifier with SCR, then it will be very controlled, very precise. The output voltage can be controlled very nicely. Second one, DC to DC converters, which are called as choppers, can be made using SCRs. Then DC to AC converters, which are called as inverters, can be made using SCRs. Then you can have it as a static switch. You can use it as a switch. You can use it in battery chargers. You can use it in speed control of DC and AC motors. You can use it in lamp dimmer circuits where you can dim the light. You can use in fan speed regulators. You can use them in AC voltage stabilizers. These are the few applications which we have named for SCRs. Then we'll go to the next term, next active component, which is DIAC. The term DIAC stands for diode for alternating current, DIAC. Okay, so diode for alternating current, which is called as DIAC. It is a bidirectional semiconductor switch that can be turned on in both directions. Okay, both forward and reverse. It can work in both forward and reverse. The device is a member of thyristor family. Now this thyristor family will have components like SCR, DIAC, TRAIC. Okay. It is mostly used in for triggering TRAIC and other thyristor-based circuits. The DIAC starts conducting electric current if the applied voltage goes beyond a breakover voltage. There will be a breakover voltage specified by the manufacturer for a DIAC, say around a 20 volt or 30 volt. If the applied voltage between its two terminals crosses that, then it will start conducting. Okay, and it is a bidirectional. So you cannot name one terminal as anode, one terminal as cathode. Both can be working as one will be working as anode, then other will be working as cathode. So here, if you see the symbol of DIAC, so you can see this one. This is one direction in which the current can flow, and this is another direction in which the current can flow. That means the current can flow bidirectional. It can flow bidirectional. That is why the first terminal here will be called as MT1, okay, and the second terminal will be called as MT2, because one can act as a anode and one can act as a cathode. So it doesn't have a control terminal. Only when the applied voltage between the two terminals goes above some specific voltage called as breakover voltage, then it will start conducting. So as I've given in the symbol description, DIAC is given by the symbol of two diodes connected in parallel and opposite to one another and has two terminals. Since the DIAC is bidirectional, we can't name those terminals as anode and cathode. The terminals of DIAC are simply called as A1, A2, or they are called as MT1, MT2, where MT stands for main terminals. Then if you see packages in which DIACs are possible, so you can get a DIAC in this type of package, you can get a DIAC in this type of package, or you can get a DIAC in these types of packages, okay, where the two terminals, one can act as an anode, one can act as a cathode, means one will be positive, one will be negative. So anyone can be made positive with respect to the other, and it is a bidirectional device. So if you go to say applications of DIAC, the DIAC are used as a trigger device in various applications such as number one, phase control circuits of motor, speed control, then light dimmers, heat controls, and many other control circuits can be applications of DIAC. Then we'll go to see the fourth active component of this section, the TRAIC. TRAIC is an important member of thyristor family of devices. It is a bidirectional device that can pass the current in both forward and bias. Same like DIAC, it can pass both forward and bias bidirectional. But here there will be a control element. The third terminal will be there, and hence it is called as an AC control device. The TRAIC is equivalent to two back-to-back SCRs connected with one gate terminal. So you can see the symbol of TRAIC here. So you can see that these are two SCRs which are connected in anti-parallel. Okay, and then one terminal is named here as MT1 and the other terminal is named as MT2, and you have a common gate terminal, okay, which can control the flow of current between the two terminals. So both can act as anode or both can act as cathode. So if one is acting as anode, the other one will act as cathode. So either the current will go like this or it can go like this. So bidirectional, and you can control the current also with this gate terminal. So if you see our packages of TRAIC, then the first type is pin standard type. In the standard type, TRAIC will be looking like a small IC with 3 pins where MT1, MT2 and gate, and a heat sink also is there on the top. So here you can see this is the heat sink. This is the heat sink and these are the 3 terminals. Okay. And these types of TRAICs are used in domestic electronic appliances. Some of the common packages are TMA36SL, TMA54SL, TMA84SL, TMA124SL, TMA126SL, TMA2065SL, TMA1065SL, etc. Then we'll go to the second type, which is called as capsule or disc type. In that, you can have a shape of the disc with extended wires to the terminals. These TRAICs have a high current capability and are made with ceramic seal. Some of the common packages of disc type TRAICs are available in the market and are called as KS100A, KS200A, KS300A, KS500A, KS600A, KS800A, and KS1000A. Then we'll go to see the stud type. The stud type or TRAICs are mostly used in high power applications. They have screwed bottom that acts as one of the main terminals and has two terminals on its top, which are the other main terminals and the gate. So here you can see this type of package. Okay, so here you have a bottom screw that acts as main terminal. So here you can have a bottom screw here. This will be acting as one of the main terminal, and you have two terminals on top. So here you have on top two terminals which can act as gate and another main terminal. These are the two terminals which can act as gate and another main terminal. Some of the common packages available in the market are TO118, TO93, TO48, TO94, TO48, TO65, okay, and RSD7. Then if you go to say applications of TRAIC, there are many applications, few are mentioned here. TRAICs are used as AC power controllers, fan controllers, heat controllers, for triggering device for SCRs, light dimmers. It can be used as a switch. It can be used as phase control applications. Thank you, students.